It's with great pleasure that I introduce Dr. William Busler. He is a former faculty member here at Christian Brothers University. He taught here for over 30 years. He got his Bachelor of Science from Christian Brothers College and his PhD from the University of Tennessee Health Science Center. He is an expert in the area of astronomy. He served as president of the Memphis Astronomical Society. He's published books on several different topics related to astronomy, as well as articles, and he's spoken around the world. And it is with great pleasure that I welcome Dr. Busler.
Hey, thank you, Dr. Miller. It's always nice to be asked back to my alma mater. It's actually, I went to the high school here as well, so when the former Kenrick Hall was the high school. So I was on this campus from 1958 to 2011, except for a few years in graduate school, almost continuously. I don't know if anyone has ever broken that record or not. If you all study hard, you should get out of here in a lot less time than that. Okay, today we're going to talk about the message of Starlight, that is what we learned from the stars by analyzing their light with spectroscopy. We would know a few things without spectroscopy, but not nearly as much as we actually know today. Okay. We would know the motions of the Earth. We could figure out that the Earth rotates and moves around the sun. We could tell that without spectroscopy. Hipparchus measured the magnitudes and positions of the stars back 100 years before the time of Christ. So we would know that. We would know from using our big telescopes a lot of the physical characteristics of the sun and moon and planets in our solar system. And we did, in fact, figure out the laws of planetary motion from the data obtained by Tycho Brahe in Denmark and the analysis of those by Johannes Kepler. We figured out the laws of planetary motion, all without spectroscopy. We could figure out distances and masses using Newton's ramifications, or elaborations rather, of Kepler's planetary motion laws. We could do that within the solar system. And we could even measure the distance to some of the nearer stars using the parallax method of the changing position of the Earth in its orbit around the sun during the year. So those things can be done without spectroscopy. In other words, we would know what the ancients knew up through about the end of the 1700s. And that would be, of course, we know what Galileo and Kepler did. Bessel was the first one who reported measuring the distance to a nearby star using the parallax method. So that's the kind of thing we could do without spectroscopy. Isaac Newton was kind of the transition between the old astronomy and the new. He used a prism. He was the first one to realize that sunlight existed as a combination of colors, all the colors in the rainbow. When he passed sunlight through a prism, he'd see a rainbow on the wall behind him. And I think you're all familiar with this. The range that the human eye can see is around 400 to 700 nanometers. And of course, there's a lot more to the electromagnetic spectrum than that, but we can't see it, not the way our eyes are set up. Honeybees can see farther into the ultraviolet part of the spectrum, and other things like certain snakes, pit vipers, can see or sense radiation into the infrared. But with our eyes, we're about 400 to 700, which is a tiny fraction of the entire electromagnetic spectrum. One time, Isaac Newton took advantage of an unfortunate situation. He passed light through a little hole in his window shade and got a much better spectrum than he had before. Well, how did he happen to get a hole in his window shade? Well, you may think that drive-by shootings are kind of a modern phenomenon in our society, but one night there was a gunfight outside Newton's window. and a stray bullet went through his window and punched a little hole in his window shade, and the next morning he held his prism up to that and got a better, clearer spectrum than he'd ever had before. There was a bunch of little overlapping colored circles rather than the lines we're familiar with. But he never pursued that idea any further. If it had been a knife fight and someone had thrown a knife through his window shade, then we would have had a nice little slit there, and spectroscopy would have been advanced by about 100 years just overnight. But unfortunately, that didn't happen. So he didn't pursue this any further, and neither did anybody else for more than 100 years. Just wasn't any demand for it. Nobody with any great mind was thinking about it then. William Hyde Wollaston, who was an English chemist, in 1802, observed some dark lines crossing the solar spectrum. People did look through prisms at the sun and noticed there was a rainbow effect there. And if you look very closely, you can see dark lines across the spectrum of the sun. He mistakenly thought that those were some kind of divisions between the different parts of the spectrum. Different colors were separated by dark lines. That was completely off base, as we'll see shortly, but at least he saw them and recorded them. Joseph Fraunhofer, he's one of the big names in spectroscopy. He should be. He used a telescope to magnify the solar spectrum, and he found a lot of lines, 574 to be exact. And he started labeling them. You would think if he saw that many lines, he wouldn't use the alphabet, A, B, C, D, to label them, because he soon ran out of letters. But he did label a lot of the lines, and we still use some of these, like the D line in sodium, the bright yellow line that occurs when you sprinkle salt into a flame. Next time you're in the lab and your teacher's looking the other way, just sprinkle some sodium chloride in the Bunsen burner flame, and you'll see this bright yellow light, which Fraunhofer referred to as the D line of sodium. Here is Fraunhofer's spectroscope. First of all, you notice that he couldn't have just called up Fisher Scientific and ordered this thing. This all had to be handmade. Look at all the detailed, beautiful work there of all these brass components that were put together by hand. And here is Fraunhofer's drawing of the solar spectrum with a list of the different lines as far as he went, and a diagram of the intensity of the sunlight at different wavelengths. Then he used a 4-inch refractor telescope with a prism. Now that's a pretty big sized telescope. A 4-inch diameter lens gathers a whole lot of light compared to the eye. And so he was able to observe a lot more lines. And he noticed when he looked at other stars, that was a big enough telescope to gather a lot of light from some of the brighter stars, not just the sun. And he noticed that they had dark lines on them too, but the intensities of those lines would vary from one star to another. So he thought he might be on to something then. He also noticed that the spectrum of the moon was the same as the sun. Well, that's kind of a duh, isn't it? It shines by reflected sunlight, so you would expect the light reflecting off of the moon from the sun to be pretty much the same as the sunlight. And then he gave that up, went back to making telescopes, which was his true love. So spectroscopy just sat still for about another 40 years. Meanwhile, other European chemists and physicists started studying the spectra of elements in the laboratory, looking at flames typically. You'd make up a solution of a salt of some element and stick a platinum wire in it, get a little droplet of that solution, and stick it into a flame. And the flames themselves in those days were bright yellow gas flames, and you could still see other colors. And sometimes if you ran the light through a prism, you would see emission lines, bright lines that those elements were putting out. And they started to come to the realization that different elements had a different signature in the spectral lines that they put out. Hydrogen, helium, all had their own key signatures, and we'll take a look at some of those today at the end of the presentation. Those of you who don't have a lab right after this can come up and take a look at actual spectra of an incandescent lamp, a hydrogen lamp, and a helium lamp, and see the differences between them. Especially active in this area were a couple of fellows, one much taller than the other, as you can see, sort of the Mutt and Jeff of spectroscopy. Robert Bunsen, who's the founder of the Bunsen burner, and Gustav Kirchhoff. They partnered up for the study of spectroscopy back in the mid-1800s. They built a sensitive spectrometer in Heidelberg in 1859, and you might want to just consider that as the beginning of real spectroscopy. Other things are kind of accidental discoveries that came and went, and different people saw different things and then gave up and didn't look anymore. But this is where spectroscopy started in earnest in 1859. Of course, by that time, we had a Bunsen burner, which was built for this purpose. Have you ever wondered why a Bunsen burner is like it is? Before that, gas was used and burned, but for illumination. Houses had gas pipes running through them and little valves, and you could light a little burner there, but the flame that came out was sooty and yellow. The reason for that was that's what they wanted, the illumination from all the light. Bunsen wanted a flame that was hot but didn't have a lot of color and light of its own. So his invention was to bring air into the gas mixture going up to the burner so that it would burn much hotter. And you know, that yellow color comes from soot, carbon. It's just glowing carbon, puts out a continuous spectrum just like a light bulb filament. But he didn't want that because he wanted to look at what was coming from the elements themselves. So he developed this burner that has got a lot of uses, but his purpose was to make a colorless flame. And not too long, a year later, he discovered two more elements. In the first column of the periodic table, rubidium and cesium, he discovered those through their spectra. If it didn't match up to anything they'd seen before, then that was a new element. So it went through a whole period of time where new elements were being discovered by using a spectroscope. And they were also the first to explain emission and absorption spectra. For those of you who haven't gotten to that yet, we'll have a little bit of a teensy tutorial on that in just a moment. But first, some pictures of Kirchhoff and Bunsen's spectroscope. There's a prism inside a box, which has a cover on it that's, of course, removed so we can see the prism inside. And the Bunsen burner out here in front looks a whole lot like the ones in our laboratory, and a sample holder that would introduce the elemental sample into the flame. And the light goes through a slit in the lens and onto the prism, and then you look at the spectrum coming through the prism with a telescope. And you can look at different parts of the spectrum by turning the prism. You notice that there's this handle that's attached underneath the prism so you can turn it around a little bit. And that lets you look from one side of the spectrum to the other. When you use these, you just turn your head back and forth. But the spectroscope was adjustable through the prism. Each spectral line that you see is actually an image of the slit in the spectroscope. If you had a squiggly slit, you would have squiggly lines. If you had a round slit, like a hole, like Newton had, then all the different spectral lines would actually be circles, and they would overlap with each other because a slit gives you a nice narrow line, and then you'd have trouble seeing them. And that was the problem Newton had, which is why he gave up. If only it had been a knife fight, that would have changed everything. Bunsen and Kirchhoff confirmed that the bright lines seen in the laboratory spectra corresponded exactly in position to dark lines in the solar spectrum. So they would set up their spectroscope, put some sodium into the flame, see where the bright lines occurred, and sure enough, in that exact same position, in the exact wavelength, there were dark lines in the solar spectrum. Same with hydrogen or any of the other elements that they attempted to find. In the lab, they would also see dark lines for those in the solar spectrum as well. So that told them that those elements were present on the sun, or at least in its atmosphere. So they started out, first ones they determined were sodium and hydrogen. One day there was a fire down the street, actually about 10 miles away. They could see it off in the distance, the flames coming up, the roof material burning up. They aimed their spectroscope at that and saw a lot of spectral lines from the material that was burning up in the building. And they said, that's certainly interesting. We can tell the composition of that roof burning up 10 miles away. Why not do the same thing by looking at the stars? About 14 years before this, the great French philosopher, scientist, Auguste Comte, had said, we will never know the composition of the stars because you can't bring one into the lab and put it under a microscope or even a spectroscope. But with this insight that Bunsen and Kirchhoff had, why not the stars? Well, that one thing led to another, and eventually we got astronomical spectroscopy. They explained the physical source of the spectral lines, what's going on inside the atoms. I think by this point in the semester, all of you, even freshmen, how many freshmen do we have? No freshmen. Okay, well, all of you have had, and maybe time to forget, what goes on inside the atoms with the electrons jumping around to cause the spectral lines to be emitted. Okay, here's the little refresher. A solid source that's glowing, like a filament of a light bulb or any other glowing solid, emits a continuous spectrum. So does a glowing liquid, like molten glass or lava from a volcano. That emits a continuous rainbow spectrum. And even compressed gases, very high density gases, will emit a continuous spectrum. Even at the surface, quotes, of the sun, the photosphere, the pressure of the gas is such the atoms are so close together that it emits a continuous spectrum. If you have a rarefied gas, such as in this tube and this tube, where there are just not that many atoms, they're very far from each other, so their energy levels don't interfere with each other, then you will get a bright line spectrum, where the transitions from one shell to another within that atom cause these emission lines. And the third kind is a dark line spectrum, or an absorption spectrum, where you have something that emits a continuous spectrum shining through a gas that is rarefied but is not particularly hot and is not emitting light itself. It absorbs at those same wavelengths. So you can see that at this point we have an absorption that would be an emission if the gas were hot and glowing, and each one of those spots in the absorption spectrum corresponds to one of the bright lines if the gas were hot. So an absorption spectrum is kind of like a negative picture of an emission spectrum. And of course that tells you what elements are present. We don't learn that from a continuous spectrum. I used to wonder, kind of worry, why, if you would shine the light from that puts out a continuous spectrum through a rarefied gas, and electrons were kicked up to higher levels, so that would subtract out particular wavelengths, why, when they just fell back down again, would that not fill back in and you'd still have a continuous spectrum coming out the other side? Well, you would, except for one thing. The light that energizes these, in this case, a sodium atom, kicks electrons to a higher level, and when they fall back down, the photons are emitted in all directions. It doesn't all go straight through again and fill in where it's subtracted out. So it scatters, in a sense. The light that it was absorbing dissipates it in all directions, so we do have a gap in the spectrum right where the absorption occurred. what takes place in an atom? Like, here's a hydrogen atom in its ground state. Let's look here. There's the proton and the electron cloud around it. We can cause the hydrogen atom to get excited and go to, say, the second or third excited state. Well, what's the main difference you see between this and this? Bigger, isn't it? That's because the second shell in a hydrogen atom is farther from the nucleus than the first. So when the electron cloud is centered on n equals 2, the second shell, it's going to be bigger than when it was here. How does it get from here to here? How does an atom get excited? Well, there are three ways. One is to shine photons on it, and that will kick electrons up to higher levels. Another way is to heat it up, like sprinkling the salt in the flame. And the third way, which we don't have to worry about in the stars, is to pass electricity through it, and that also causes the electrons to get excited to higher levels. So that gets them up to a higher level, and then eventually they work their way back down. What goes up must come down, and as the excited atom goes towards a lower state, photons are given off of a particular wavelength. You've all seen the diagrams for that. In fact, this is in your Principles of Chemistry book. So is this diagram. Here are the different states: the ground state, level 1, n equals 1, the second shell, the third shell, fourth, and so on. Transitions from any one of these to any other are taking place all the time. When we turn this light on, all of these transitions are taking place, going up and coming down. The ones going up you don't see, because that's electricity causing that to happen. When they fall back down, photons are given off. Now when the electrons fall all the way back down to the ground state, so much energy is given off that it's in the ultraviolet part of the spectrum and you can't see it. Remember that, the Lyman series? When the electrons fall from any upper state down to the second shell, then photons that are visible can be seen. And this is called the Balmer series. And the lowest energy line in that is the hydrogen alpha. When we have a transition from the third to the second shell, that gives off a reddish light. When we go from the third shell to, the fourth shell to the second shell, a kind of a teal blue-green color comes out. And then the gamma is a deep blue, and the delta is a purplish blue. And eventually the lines just kind of run together. So that's what you see in the Balmer series, and you will see that when you look at this hydrogen lamp through the diffraction gratings that are sitting up here. And here's the relationship, for those of you who might have forgotten, of the wavelengths related to the energy jump. Inversely proportional. Planck's constant, speed of light in the numerator, and the difference in energy, the jump right there in the denominator. So the bigger the energy jump, the shorter the wavelength. Everybody coming back to everybody that's had that before. Okay, Louis Rutherford in 1864, notice we're moving along in the years here, followed up on Bunsen's idea. He was working out of downtown New York City, which isn't as brilliantly lighted now or then as it is now, but he photographed a high dispersion, meaning high power, high magnification solar spectrum using an 11¼ inch refractor. Now that is a big telescope. So he gathered a lot of light with that and got a spectrum of the sun. Meanwhile, in Sweden, Andreas Ångström, for whom the Ångström unit is named, is same as a 1/10 of a nanometer, he made a chart of the solar spectrum, and now with the instruments he was using, he found 1,200 absorption lines. And many of those he matched up to common elements that were found in the laboratory. So these spectral lines in the sun corresponded to this element, those corresponded to that element, and so on. By the end of the 19th century, 50 elements had been identified on the sun, including one very important one that at that time was unknown on the Earth. In the total solar eclipse of 1864, a signature of spectral lines was observed that did not match up to any of the known laboratory lines that had been discovered and cataloged so far. So they figured this must be a new element. Since we found it on the sun, we'll name it after the sun. The Greek name for the sun is Helios, so helium was that new element. It's now been found on the Earth, of course. We don't send off to the sun to fill up balloons. That usually comes from underground, from radioactive decay. Alpha particles is, the same thing as helium nuclei, so that's where most of the helium on the Earth comes from, but that wasn't known then in 1864. So now we have the solar element, helium, discovered. William Huggins, working in England, he observed the spectra of stars and nebulae. What's a nebula? Gas cloud, either where new stars are forming or where old stars have sent out some kind of either explosion or an expansion of a gas cloud around it. But nebula just is the Latin word for cloud, so any kind of gas cloud. He observed the spectrum of several different nebulae. He had an assistant chemist. It's always good to have. Physicists need chemists to kind of lead them around and show them what to do in the laboratory because they're all so theoretical. He's later assisted by his wife, Margaret Huggins, and he referred to her as a capital scientific housemaid. Now, this was more than 100 years ago. You can be thankful that things have changed in the perception of women in science since those days. Here's William, and there's Margaret. She looks like she's grabbed hold of a hot wire there, the way it's doing her hair, or maybe it's just with dealing with him for so long. I don't know. Capital housemaid. Okay. Huggins confirmed Fraunhofer's observation that the stars had spectra that were a lot like the sun, but different lines were prominent, indicating to him that there were different elements were favored in some stars over the others. He tried to photograph, see, this is kind of at the beginning of photography, isn't it? In historical context, the Civil War, the war between the states, was one of the first events that had a lot of photography going on, that 1860 to 1865. So during that time, photography was pretty much brand new, and he tried to get the spectra of a couple of bright stars, but it didn't work out. But a few years later, you just keep trying. When at first you don't succeed, what? Now, try something different. If you try the same thing, if you're a scientist, you'll get the same result. You have to believe that. So you try something different, try something better. And by that time, the plates had gone from these wet, sloppy things that had to be taken from a dark room into the telescope, still wet, still dripping, but protected from the light. That's kind of doomed to failure. But later on, they had dry plate photography, and also the clock drive so the telescope could follow the star. As the Earth rotates, the stars move across the sky. If you're trying to take a spectrum of it and it's a moving target, that's a little tricky. So they had to develop clock motors that would turn the telescope to exactly follow the motions of the stars across the sky. So a dozen years later, he tried something better, and he did succeed. He also looked at some nebulae and discovered only emission lines. Okay, what does that tell you? Let's just deviate for a second here. If the emission lines were all you could see in a nebula, that tells you they're like this and this. That is a very rarefied gas, not a solid or near solid, very dense gas like on the surface of a star or the sun. That gives you a continuous rainbow spectrum. If you only see bright lines, you know you're dealing with a very tenuous, dilute gas where the atoms are very far apart from each other. But when he looked at what was known as a spiral nebula, they had a continuous spectrum like the stars. So what does that tell you? They are like the stars. In fact, the spiral nebulae turned out to be island universes. That was the first name they came up with. But we now know that there are other galaxies like our Milky Way, made up of hundreds of billions of stars. Here's one such example, the Sombrero Galaxy in Virgo. It's an aggregation of, say, 100 billion stars or more. And what's the spectrum of that going to look like? Well, like stars, a continuous spectrum. So that's why the spiral nebulae gave them a solar-type spectrum. Okay, Henry Draper, one of the greats in spectroscopy, still working from New York, 1870. He built a couple of big reflector telescopes, a 15-inch and a 28-inch, and silvered the mirrors to make them more reflective. He used the 28-inch to photograph Vega, a bright star in the summer sky, the first spectrum to be photographed other than that of the sun. And then, like Huggins, who used the dry plates, 1879, he started recording lots of stellar spectra. He would just go from one star to another and run the light through the telescope and out through a prism onto the photographic plate. By 1882, several years later, he had 80 spectra of stars, some planets, a comet, and the Orion Nebula. This doesn't look like much today, but this is the first spectrum of the Sun and Venus on a photographic plate, which was round at that time, taken in 1876. He unfortunately died kind of young, at 45. His widow took his money and gave it to Harvard College Observatory to continue his work of photographing and obtaining and classifying the spectra. Now, they made a big breakthrough. Instead of aiming at each individual star and taking a picture of it, they put the prism over the front end of the telescope, so every star in the field of view looked like a little rainbow, and then they would take a picture of that. So that way you could get a whole bunch of them at once, and that sped up the process tremendously, and that would give a spectrum of every star. And by the 1920s, the project, the Henry Draper catalog, included the spectral classifications of more than 200,000 stars. We still use that catalog. You may have seen this if you read the online news, that somebody thinks they've discovered a planet around some star, HD 83056 or something. That HD stands for Henry Draper, who started that catalog back in the 1800s, and still use it. Meanwhile, backing up a little bit, in the 1840s, Christian Doppler and Armand Fizeau independently explained what we now call the Doppler effect. You're familiar with this for sounds. If you step out on the middle of the expressway and a truck coming along honks his horn at you, after it runs over you, you will notice that after it passes, the pitch of the horn is a little lower than it was when it was running you down. I get tired of talking about trains and things like that, which is always what's used as the example of the Doppler effect. Same thing, sound source is approaching, the waves of sound are bunched closer together, so your eardrum gets vibrated more rapidly and you hear a higher pitch. If something's receding from you, the sound waves are stretched out farther and they don't hit your eardrum as often, so you hear a lower pitch of sound. The same thing happens together with light. If you have a yellow star and it's sitting still, it'll look yellow. If the star is approaching you, the waves get bunched closer together and they appear to be of a shorter wavelength because they're hitting your retina more rapidly, and that will be more of a bluish color if that's the case. If the star is receding from you, then the light waves get stretched out and it will look redder than it should because it's receding from you. Same Doppler effect. So, already just said that. Okay. Now, not only the overall color that you see is changed if something's rushing towards you or away from you, but where the maximum wavelength is. We'll see next week how important knowing what the maximum wavelength in the star's emission is. And all of the spectral lines get shifted one way or the other. That tells you if the lines are shifted towards the blue end of the spectrum, that star is approaching you, right? If they're shifted towards the red end of the spectrum, it must be receding from you. But you know more than that. you can not only tell whether it's approaching or receding, but how fast. There's a ridiculously simple equation. Every now and then God gives us a break and we don't have something with the fourth power and 18 terms in it to figure out. Here's a very simple equation. The amount of shift in a spectral line due to the star going towards us or away from us, divided by what it would be sitting still in the laboratory, is the same ratio as its actual speed compared to the speed of light. What could be simpler than that? What could be more useful than that? We just measure the shift, compare it to the laboratory wavelength times the speed of light. That gives us the velocity, and whether it's shorter or longer wavelength tells us whether it's coming towards us or away from us. Remarkable equation. There is a more complicated version of this equation when the speed is near the speed of light, and then you have to use a relativistic version. But for normal speeds, up to maybe half the speed of light, this works just fine. Here's an example. Here's a star that's emitting a line, say at 2,000 angstroms, which is 200 nanometers in the ultraviolet. And it's moving away from us at about 20% of the speed of light. So the shift is going to be 2/10 of that. So that's another 400 angstroms, so 2,400 would be the wavelength. It's lengthened by that amount. I'm not going to try to do the rest of these in my head, but see, here's one I can do, 5,000. 20% of that is 1,000. So it's emitting a line at 5,000 angstroms, but we see it at 6,000 because it's stretched out wavelengths longer. Here's a spectrum of a quasar, which we'll see a little bit more about next week, and the spectral lines from hydrogen in the laboratory standard. Here's the beta, the 4:2 transition, 5:2, 6:2. Those should be here, here, and here. But in this quasar, this is shifted down to here, and this is shifted down to here, and this is shifted down to here. Greatly elongated because the quasar is receding from us at a very high speed, 16% of the speed of light. Okay, back to Huggins again. He had detected spectral line shifts, not just the lines, but shifts in the lines of several bright stars. And 1888, Hermann Vogel photographed some of these stellar spectra and measured the shift in the lines. And from the equation we saw a couple of slides back, he calculated what we call radial velocities. That means going towards us or away from us as opposed to crossways. You can't measure that this way, but the receding or approaching, he was able to measure. By the 1890s, William Wallace Campbell at Lick Observatory near San Francisco published the radial velocities of thousands of stars. And he concluded that the stars in our Milky Way galaxy were speeding through space at many thousands or hundreds of thousands of miles per hour. Part of this is due to the rotation of our galaxy, but with differential rotation, faster near the center, slower out towards the edges. But part of it's just kind of a random meandering of the stars that they're not all just stationary. They're not following an orbit exactly around the center, but they're wandering around a little. So that was kind of interesting when that was discovered. Notice concentration of stars toward the center, spiral structure related to the galaxy's rotation. More about that next week as well. William Henry Fox Talbot. If somebody's got 4 names, you can be pretty sure they're British. So he's an inventor. In 1871, he predicted that some binary stars could be detected by oscillating shifts in their spectral lines. Well, what's a binary star? It's 2 stars in a fixed system orbiting around each other. Sometimes you can see them, like the nearest, one of the nearest ones is Sirius, the brightest star in the sky. It has a companion that orbits around it. You can see that. But Mizar, in the handle of the Big Dipper, the star looks like a single star, but it has spectral lines that seem to shift back and forth. And that tells you, if you're thinking that the 2 stars are orbiting around each other, and we're looking at it kind of edge on. So when one of them comes towards you, its lines are blue shifted, while the other one's red shifted. Then when they're going across your line of sight, they're back where they're supposed to be. Then they trade places, and the one coming towards you is now blue shifted, the one going away is red shifted. So you see that going on. You can learn a lot about the binary star. So it sometimes had double spectral lines. When one's coming towards you, one's going away. When they're side to side, you don't see that. And after studying that, Antonia Maury found that Mizar A's period 20.5 days for the two stars to go around each other. And while they were at it, they looked at the other component of Mizar and found that it was also what we call a spectroscopic binary. You don't see two stars there in the telescope, but the spectrum tells us that it really is two, one orbiting around the other. And then it started to turn out lots and lots of stars were binaries. Now we think that maybe 2/3 of stars are binary, and the rest of them probably have planets. So the single isolated star is a very rare thing if it exists at all. I forgot the olives. Okay, so putting this together with Kepler's laws of motion and Newton's derivation and explanation of them, then we could start to determine the masses and separations of binary stars using spectroscopy. Isn't that amazing? Here's Newton re-derived Kepler's laws, which were obtained from data. Newton derived them from scratch, had to formulate the theory of gravity to do that, and the inverse square law of gravitational attraction. But once he'd done that, he came up with Kepler's laws of planetary motion. Here's the basic Kepler's law as derived by Newton. Here's the mass of the sun and the mass of the planet. And these are the distance of the sun and the distance of the planet from their common center of mass. Now, you may not think about this, but does the Earth revolve around the sun, or vice versa, or some other thing? Yeah, some other thing. They both revolve around their common center of mass, which in the case of the planets and the sun is inside the sun, but not in the very center. The sun itself ooches back and forth a little bit as each planet goes around it. So that's what this is the distance of the sun from the center of mass. And Kepler's original law was just p squared equals d cubed, because the mass of a planet is tiny compared to that of the sun. So all we have on this side left is the mass of the sun, and if that's in solar masses, how many solar masses does the sun have? Well, 1, so that's p squared on the left. On the right, if we ignore that distance, then that's the distance of the planet from the sun, essentially, cubed. So that was the original law, but here is Newton's amplification of it. So here's where it comes in with spectroscopy. We can use those equations to calculate the masses of the binary stars, and even later on we'll see entire galaxies. Looking at the equation again, now we've got one star and the other, and one star and the other, and the distance from their center. Sirius, A and B, we've already talked about that, the brightest star in the sky. It's a double star, and you can see it, the little one moving around the big one. The white dwarf orbits around the big white star. Using this equation and knowing the distance between them, we can calculate that the sum of the two masses is 3 solar masses. So those two stars put together weigh 3 times as much as our sun. Okay, that doesn't tell us either one, but what does? How much they move. If we watch them, we see that the little white dwarf moves twice as much as the big star. What does that tell you? The big one is twice as much as the little one, right? In other words, the big one is 2 solar masses, the little one is 1. The total is 3. And that's how we know it, because we can see that. But what about one of these we can't see? Then spectroscopy comes in. The distance we can see in a telescope on Sirius can be determined by the spectral shift. So the ratio of the masses is the same as how much the lines in the spectrum shift, because that tells you how much they're moving. The little one moves more than the big one. Well, that tells you that the shift of that one is the opposite of its mass. The one with the more shift has the smaller mass. So they're just a little simple equation tells you that. So we can get the masses and the separation of any double star system using spectroscopy to measure the shifts in the spectral lines and Newton's brilliant derivation of Kepler's laws. So astronomers started to need more and more light to obtain the spectra of fainter objects like remote galaxies. Like any scientist, you're always asking for more money, because if we get this, we can go to the next level and our knowledge will be expanded therefrom. You might as well get used to doing that, whether you're a doctor in practice or a scientist in a lab. You're always asking somebody for money so you can do just a little bit more. In the 20th century, astronomers demanded and got bigger and bigger telescopes. Ultimately, Edwin Hubble used spectroscopy to discover the expanding universe. We'll go into that in some detail next time. And that led to the Big Bang theory, which he didn't propose. I'll tell you then who did, and it's not who you think. Maybe somebody you had never heard of, but we'll get into that. Okay, we will take a brief 1-week intermission and hope to see you back here then. Meanwhile, what I'm going to do is turn these on, and if you don't have a lab coming up right away, come up and take a look at what we've been talking about, the continuous spectrum from the light bulb filament and the bright line spectrum from the helium or hydrogen and the bright line spectrum from the helium light. I'd like to introduce a couple of people before we break up. One is Ric Honey from the Memphis Astronomical Society, who maintains our web page and records all our presentations for posteriority. And another is Annalise Hosey Sowell, who is one of our chemistry graduates from years ago, who is now the head of the science department at MUS and has shuffled her lunch period around so she could be here to see us. And she and her husband contributed the money which we use to get these little devices here. So we're very grateful to her for that. So thank you for your attention today. Tell your friends and come back next week, and we'll finish up with a lot of astronomical applications and how we know the age of the universe and the Big Bang and all of that, all from spectroscopy.